So plate tectonics and volcanism. When you look at this picture, the first thing you see is green and blue, of course, the continents and the oceans. And the continents are largely made by subduction zone volcanism. But that's a complicated thing, and I'd rather stick to something simple. So I want to motivate what I'm going to say by mid-ocean ridges. And in any case, there's about 80% of the global volcanism is at mid-ocean ridges. And they resurface 2/3 of the Earth every 100 million years. So these are very, very active places where melt is produced and migrates to the surface. And for those who don't know, these are the boundaries between two oceanic plates that are diverging, and so new real estate is being created at these faint lines in the middle of the ocean. And if you kind of cut through this plate boundary, what you would see is a spreading center, a mid-ocean ridge here, where the lithosphere, this sort of rocky, very highly viscous, cold part of the mantle, is spreading to the left and right due to stresses which come from the negative buoyancy of the slab as it sinks back down into the mantle. And where they are pulled apart, they induce mantle upwelling, and we'll talk about what happens next. Of course, subduction zones are also fascinating and really a topic of current research by a number of you. And I'm sure we'll be hearing about that this week. So with apologies to many of you, here is the mantle. It's a rock that's composed of dominantly a few kinds of minerals, and this is oversimplified grossly, but olivine is about 70%, and if you're not a petrologist, you can think of this as kind of an inert phase. It doesn't really melt. It gives you most of the properties of the mantle, its permeability and its viscosity and so forth, but it doesn't participate very much in the melting process. This is really the stuff that melts, the pyroxenes, and there's a compositional range of pyroxenes, but never mind that for now. It's about 1/4 of the mantle, and it has a lower melting temperature, much lower than olivine. And then there are some aluminous phases, meaning they have aluminum, and at different pressures, and they take different forms, but in any case, they compose a small amount, but they have important chemical properties that affect the way that chemistry is transported by magmas. And those things are ground up and packed together in peridotite, which is the kind of generic rock that is in the mantle for the mathematicians. Grain sizes of peridotite can range from less than 1 millimeter to bigger than 1 centimeter, which has very important implications for rheology and permeability. So the mantle is inaccessible, and one of the ways that we know about it is by studying it in the laboratory. And I'm not going to talk a lot about all the laboratory work that's been done, but here are some classic experiments in the 90s where mantle rock was subjected to high pressures and temperatures, like what they experience in the mantle, and enough to produce melting, and that melt was squeezed out into a melt trap up here, composed, I think, in this case, of diamonds. And then the melt was measured for its chemical and physical properties. And the reason that they could squeeze the melt from this source and into the trap is because when it forms, it creates a permeable network at the grain boundaries of the mantle. So what's shown here are the pore spaces, which are formed by melting of some of the minerals in here, the pyroxenes mostly. And the olivine grains have been made transparent. So you see right through the solid, and you just see the liquid phase in the pores. And even at low porosities, you can see this connected pore network. And the grains are all different shapes, but we can idealize that a little bit into grains that are called tetrachydecahedron. Never mind the name, but these are objects that can tile three-dimensional space perfectly. So you can fill up 3D space, and they have these facets, and they have triple junctions where 3 grains are adjacent, and quadruple junctions where 4 grains are adjacent. And because of the unsatisfied bonds along these junctions, that's where the melt likes to sit. It likes to wet the grain boundaries, especially at quadruple and triple junctions. And because of those wetting properties, which we'll discuss in a minute, these pores, even at low porosity, will be connected. And so if we make a slice across like this through this triple junction in this pore throat. Without the magma, what we see is triple junctions and double junctions in 2D. And it's very much easier to talk about the pore structure in 2D. So here's a plot of 1 grain, 2 grains, and 3 grains at a triple junction with a pore of magma that we've cut through. And the pore takes its shape because the dihedral angle, which is given by theta, which results from a force balance of the tensions on the liquid-solid and the solid-solid contact. So you do a little force balance there. You can compute this dihedral angle. And then the shape of the pore is otherwise a constant curvature surface, which comes from minimal surface energy constraints. And of course, when you look at natural rocks, it's rare that you see something quite like this. But on average, in some sense, this is what's going on at the microscopic scale, dominantly controlling the connectivity of pores, and is what explains why, when the mantle melts, that melt actually escapes and comes to the volcano. So some more recent calculations using the same shape grains, but in 3D from Marques's group in Texas. And you can see this is at porosity of 1%. So as long as the dihedral angle is sufficiently small, and 60 degrees is, I think, roughly a cutoff for most porosities, then you can get connectivity of this pore network. And Wenlu Zhu, who was here for the earlier workshops, I don't think is coming to this one, and her group have looked at microtomographs of olivine liquid aggregates. So this is only a few, maybe a millimeter or so. Olivine grains, and the pore spaces have been removed. So and they've done a calculation of pressure-driven flow in the pore space. And then by computing the sort of volume average flux, we're able to work out the porosity-permeability relationship. So this is a plot of porosity versus permeability on a log-log scale. And there's their data, and a power law fit through it with an exponent of about 2.7. And the vertical offset here is due to grain size, and they use very small grains, of course, but in the mantle, grains may be larger. And this is consistent. What they found is consistent with what the canonically has been assumed about mantle permeability on the basis of a variety of different experiments and calculations. But that is that you've got this power law with an exponent that's between 2 and 3. And so what I've shown here is the solid line is for 2.7. These dashed lines, this dashed line is for 3. Typically, we parameterize this in terms of a power law on porosity, grain size squared, and some constant, which is empirically determined. And beneath the mid-ocean ridge, the plates, of course, are spreading, and we can think of this as a 2D cross-section with gravity pointing downward, and mantle is drawn up. And as it decompresses, it melts. Effectively, this is an adiabatic process. That is, advection is much faster than diffusion, and so you're not adding heat to the mantle to cause it to melt. Instead, what's happening is this is the adiabatic decompression path in a temperature versus depth. So a parcel of mantle rises along this path, and instead of adding heat, you're reducing the melting temperature, because the melting temperature of the mantle is pressure dependent. As you go to greater depths, the temperature of melting is higher, and so at a certain point, with upwelling, the mantle is above its melting temperature, and it melts. And then to sort of jump ahead, these principles, permeabilities, viscosities, and melting temperatures, can be combined with conservation statements and discretized and solved numerically to go from the cartoon, which I showed you before, to sort of quantitative models of mid-ocean ridges. So here's a slow spreading ridge and a fast spreading ridge. These are temperature contours. These are streamlines of mantle flow. And these white particles are moving with the melt where it's present, and where the melt is not present, they're moving with the solid. And I don't think that this is showing you a whole lot that's new relative to to what was already known, but the point is that the ideas that people have thrown around on the basis of petrology, of seismology, of analytical fluid mechanical calculations are well represented by more complicated models in which melt transport is taken into account, and simple models of petrology. And so this is not really an end point, but a starting point. So this is, it looks a lot like the cartoons, but what we'd like to do is go a lot further than that so that we can begin to make comparisons with the geochemistry and the seismology and so forth. This is a kind of, I would almost say, like a classic result in that it starts from some fairly basic assumptions about conservation, about petrology, and reproduces the sort of the basic behavior of mid-ocean ridges. So let's try to now connect the dots from the material properties that I showed you to this numerical model, and then look at what the challenges are. So here are the governing equations, and I want to say that although we're all here because we're interested in, not all of us, many of us are interested in solving these equations. Really, we shouldn't take this for granted. This is not a theory which is proven to be correct about the Earth. I would say, certainly conservation is not something we're going to question, but there are a lot of details, and whether these incorporate all of the relevant physics, I think, is not guaranteed, and that's crucial actually, because we don't want to assume that all of the behavior of the Earth is going to be captured by these models. In fact, maybe the most interesting thing is what these models don't capture, and therefore how do we refine them to be more correct and more representative. But here's what we've got from really 1984. The top two equations are the conservation of momentum equations, and the bottom two are the conservation of mass equations. So this one looks like Darcy's law in that you've got pressure gradients and body forces driving segregation of liquid from solid. There's the permeability and the viscosity of the liquid, and this is a segregation flux. The second equation looks like Stokes. So here we see gradients in pressure, but this is the liquid pressure. This is the deviatoric part of the strain rate, and here's the isotropic part of the strain rate. And C is the compaction rate. So this is the dilation or compaction of the solid grains as they imbibe or expel melt. And that's a really crucial feature of this system of equations, which differentiates it from a lot of other equations, that compaction is actually a fluid dynamical process, or a poro-viscous process in some models, which is fundamental to transport of magma, and really makes a lot of this mathematically interesting and different from everything else. And here are the body forces which drive mantle convection. So that's the bulk or phase average density. And then because there are two phases, you also need two mass conservation statements. And this one says that as you track a parcel of solid mantle as it moves through, say, a mid-ocean ridge or a subduction zone, its porosity changes. And it changes because there's melting taking place. So, some of the solid is being converted to liquid or vice versa. And because there's compaction. And so, these are the two fundamental processes that need to be understood. The mechanical part of porosity change and the thermochemical part of porosity change. And this is a kind of continuity equation, which for certain assumptions, which we'll hear about probably over the course of the week, Boussinesque approximations, where we're going to throw away density variations when they're not multiplied by gravity, when they're not part of the body force, takes this simple form. And what this says is that the divergence of the liquid flux or the solid flux can be non-zero, but when you phase average these two, the gross material flux, the bulk material flux divergence is zero. So there's that kind of continuity in the context of the two-phase flow. So some key notation with, again, apologies to those for whom this is oxygen. The porosity phi is a volume fraction of the liquid phase in a kind of representative volume element. So we're homogenizing over, or we're coarse graining over a bunch of grains where, Some pores have a lot of melt and some have less, but we average over that to get a continuum property. And then there's a solid or matrix velocity. Many people will call this V sub m for matrix. And that's the creeping velocity of the solid mantle. So in the context of the Stokes flow of the mantle, and VL or VF, if many people will refer to it, is the Darcy flow velocity of molten rock through the pores. And then there's this crucial symbol C, and maybe there'll be other symbols that are used for this, but the compaction rate is the divergence of the solid velocity. And if you think, well, why is it called the compaction rate if it's the divergence? So when you have a positive divergence, then that's really a dilation rate. But this is the convention that's been in the literature, and I think most people stick with it. So when you hear the compaction rate, it's positive div V, even though that's actually dilation. Don't get confused. Yeah, I wasn't going to say it. I wasn't going to say it, but actually Mark's responsible for most of these mistakes. Gamma is a melting rate, and beneath this one symbol gamma lies a whole field of thermodynamics and petrology, which is enormously complicated. And I don't think anyone in the audience here has devoted their life to understanding this, but we probably won't have any detailed treatment of this. And then there's the constitutive laws, the rheology, and that will play a huge role in the talks this week, I think, because there is no sort of conservation principle well, of course, underlying all of this there are conservation principles, but these tend to be empirically formulated, and for the Earth, simplifying complicated material behaviors. And they do actually have very important implications for the behavior of the solution, even if everything else is just conservation of mass, momentum, and energy. And this overline typically represents a phase average, where we take a liquid property and a solid property and add them up in this way. And what everyone should be aware of, if they're not already, is that if you take this system of equations and you look at the limit where the porosity, the melting rate, and the compaction rate are all 0, then the difference in pressure between the solid and liquid phases becomes 0. Oops. And, sorry. The liquid, the pressure difference becomes 0, so the solid and liquid pressures are equal, and the equations reduce to incompressible Stokes. So that's one limit of these governing equations. The other limit is Darcy's law, and that's where you have a rigid matrix with Vs is equal to 0 and ignore compaction and melting. And you can eliminate the liquid velocity, and many people will do this. And when you're looking at analytical solutions, it's almost always the case that you would just algebraically manipulate the equations. You see that VL has dropped out, and we've thrown away one of the mass conservation equations. You can formulate this different ways, but because you've lost one of the variables, you need a smaller set of equations. So some simple problems that will help us to understand the behavior of the equations. One of the simplest ones, I think, is the compaction press problem. And in this case, we've got a column of partially molten rock, and it's being pressed against a sort of filter, which allows the melt to go through, but the solid is prohibited from going through this boundary. So the melt can move freely through. And then we impose some far field velocity on the solid W naught. And very, very far from this boundary, the melt and the solid move together. They don't know that the boundary exists. We can think about this going off to infinity. And so very far, the material doesn't know that the boundary exists, and melt and solid move together. But at the boundary, obviously there's segregation. And so the question becomes, well, how far away from the boundary is the boundary felt? How far away from the boundary are the liquid and the solid seeing this difference in permeability or in mobility? And the answer is the compaction length. And the compaction length is an inherent length scale in the system of equations, which is a combination of the the viscosities. This is the compaction viscosity and the shear viscosity and the liquid or magma viscosity and the permeability. And this is an inherent length scale which tells you something about how perturbations to the pressure difference, so here's a perturbation to the pressure difference. The liquid has atmospheric pressure, say, and the solid has something else, will propagate or be felt by the medium. And the solution, skipping all of the analysis, looks like this. This is the compaction rate, so this is the pressure difference between the two phases. It's the dilation or compaction of the matrix is dropping off exponentially as you go away from the boundary. So here it has a value of -1, so the solid is compacting and the liquid is moving out. And back here, the compaction rate is 0. And we make that transition of order a couple compaction lengths. So this is the distance normalized by delta. And so the compaction length emerges as this characteristic length scale in the problem. And here's another classical problem from Mark 93, where you have a step in porosity. So this is the independent coordinate here. And you go from higher porosity to lower porosity, and therefore from higher permeability to lower permeability. And gravity is pointing to the left, and so the liquid or the magma is segregating to the right. And this discontinuity in the permeability leads to a pressure and a compaction rate which are localized around the step in permeability. And that perturbation to the pressures decays as you go away and off towards infinity in either direction, and the length scale over which it does so is the compaction length. And so the compaction length, again, is a key length scale. Another canonical problem is the solitary wave. So when you add time dependence to the problems that I've shown you, what you would then ask is, okay, suppose you do have this pressure perturbation. Well, can it move through the medium? And it can. And in fact, if the porosity profile has this characteristic shape, which is the magmatic solitary wave, then it can propagate without changing its shape. And this has been something that many people have studied. It mostly goes back to Barcelona and Richter. This is the compaction rate, which is a consequence of this porosity profile and allows it to propagate. So here are just some movies to wake you up. This is the propagation of a single solitary wave. As you can see, it propagates without changing shape. It does so because it has this very particular analytical form. And when two solitary waves interact, they do something quite magical. They can change positions because larger amplitude waves travel faster than smaller amplitude waves. And so the big one catches up with the small one. And you can see that the big one has actually traveled faster in the same amount of time, further in the same amount of time, because of its interaction with the smaller wave. It was a combined larger wave at some point, and it moved a little bit faster. And these are sort of special features, but in fact they are, because they're natural solutions, they can emerge in more general situations. And so it's important to keep an eye out for this, because if you aren't aware of what these things look like, you might confuse them for numerical instabilities or noise, when in fact what you're looking at may be a feature of the solution of a problem. So here's a case where you have a sort of smoothed out step in porosity, and this generates a wave train of solitary waves. And again, it looks a bit like numerical instability, but it's not. It's a characteristic feature of the solution of the equations. And Mark spent much time looking at how these 1D solutions can be or can't be looked at in 2 and 3 dimensions. And in fact, there are characteristic solutions in 2 and 3 dimensions, but they're different from the 1D solution, and they have some very different properties. And the 1D solution this is a 2D solution, is unstable in 3 dimensions and breaks up into 3D solutions. So these are really important and characteristic features of the equations that can emerge in more complicated cases. mantle deformation in the laboratory is another really important aspect of these problems, because it gives us a chance to validate the theory and the constitutive laws. And so I think being aware of these experiments is really important for anyone in the community. This is an experiment from Dave Kolstad's lab in which initially uniform mixture of olivine and basalt was brought up to the pressures and temperatures at which the basalt became molten and the olivine remained solid, but the porosity was roughly uniform. And then a simple shear was imposed on the system, and after a certain amount of strain, the experiment was quenched, and the porosity pattern locked in and then analyzed by sectioning and microscopy. Here's another case where the deformation was performed by twisting the sample, and the cut is tangential, but along this tangential cut, it's more or less simple shear. And so the behavior is quite similar. The initially uniform porosity has changed with strain into this highly localized porosity pattern of bands which are at low angle to the shear plane, and compacted regions in between where the porosity has gotten quite low. And here's a zoom of one experiment from Ben Holtzman and Dave Kolstad, and these cracks can be ignored. They're just an artifact of decompressing the experiment at the end to quench it. But what you can see are these bands. And the really amazing thing about these experiments is that effectively, no matter how much they strain them, the bands always stay at roughly 15 degrees or 15 to 20 degrees to the shear plane, even though you would think that they would be rotated upwards to higher angles by the flow, which tells you that there's something actively taking place that as bands get rotated, they reform at low angle. And the theory ought to be able to capture this, and we ought to be able to model this, and if we can't, that tells us that we've got something to learn from the experiments. This is just a histogram of band angles from 0 to 40 degrees to the shear plane, and you can see that they're tightly clustered between 15 and 20 degrees. And here's a tangential section from torsion, and just a cartoon from Mark's work to say that we would expect that when simple shear is aligned with the bands angled, to the left, let's say, in these pictures, that there's tension across these weak bands, and therefore you'd expect low pressure and the melt to flow into them. Whereas if the shear and the band are oriented as they are in this picture, then there's compression across the band, and you'd expect the melt to be expelled. But this kind of simple cartoon would lead us to think that 45 degrees is the angle that you would see bands, because that's the principal component, the direction of the maximum tensile stress in simple shear. But that's not what you see. So there's some that tells you something. So this has been studied using linearized stability analysis, and I'm going to spare you all the details. Many of you would know them anyway. But you take a background state of simple shear, and you impose some small perturbations in the porosity, and you orient those perturbations however you like, and you ask whether they grow or decay. And so here's the terminology. There's a plane waves with a wave vector and an angle theta to the shear plane, and that wave vector is imposed initially, but it also rotates in the flow. And one of the first things that comes out of these calculations is that, from a theoretical perspective, you would think that only perturbations which have a length scale, this is L, the wavelength, versus the compaction length, which is smaller than the compaction length, would have a positive growth rate. Would have a growth rate. So you would think that if the compaction length is too small, that you wouldn't see bands growing. If your perturbations are larger than the compaction length, then the growth rate is nearly zero. Whereas if the perturbations are smaller than the compaction length, then you would have the emergence of this structure, and that's fine, except for the experimentalists, to produce those features, had to add chromite to their experiments to try to reduce the length of the compaction length. So there's some question, I think, although we can do a lot in modeling these, there's still some question about this very, very basic result and how this can be reconciled with the experiments. Of course, the angle is also a key parameter. Here's theta, the band angle is, and then the growth rate as a function of band angle. And so this is where you're down in this regime where you have small wavelength relative to the compaction length. And the observations, remember, are about 15 degrees. And for Newtonian viscosity, that's porosity weakening, where the bands are weaker simply because they have more melt, you expect 45 degrees as an instantaneous growth rate. And if you look at a non-Newtonian viscosity, then you see that with increasing sensitivity to the stress, that you can find bands at low angle. Well, we'll come back to the but. And of course, bands get rotated with the flow. So this is, even, if you just consider these to be material lines that were just painted onto the simple shear, they would be advected by the flow, and their angle would evolve according to this formula. And the trajectories are plotted here. So this is the initial angle, and then with increasing shear strain, how that angle evolves. And we see that low angle bands tend to remain at low angle, whereas high angle bands get rotated. So this is a funny feature of simple shear. But what that means is that you can take the growth rate, which we've computed, and integrate it over time to get the amplitude of bands. And here are a couple of plots showing that. This is for the Newtonian case and the non-Newtonian case. So we saw 45 degrees initially, and that it evolves to higher angle, not as fast as the passive advection would lead you to expect, but it does evolve to higher angle. And that's not consistent with experiments. Well, for non-Newtonian viscosity, the peak is much lower angle, and this led us to think that maybe this would be consistent with experiments. Now, the experimentalists from the beginning said, well, sometimes we do experiments which we know are not in the non-Newtonian regime, and we still get bands. And so this proved to be wrong. I mean, it simply can't be correct that you need an exponent of 6 non-Newtonian viscosity. And ideas have evolved a lot since then, grain size, damage, anisotropic viscosity, and it remains a very active research area. And then, just to wake you up, I want to show some movies periodically. So these are, I'm not going to talk about anisotropic viscosity. It would really require a full hour in and of itself. But these are for anisotropic viscosity, and you can see for simple shear and for torsion that small perturbations will grow into low angle bands. And that seems really great, except for that there are real problems here, like why do experiments have bands that are only about 20 to 25% porosity no matter how large the strains are, whereas in these models you can run them and the porosity will continually get larger. So there are challenges in understanding what physics is missing from the models to reconcile that once again. And lastly, we come back to mid-ocean ridges and look at corner flow. And this is a classical fluid dynamical result. So in the simplest way, there's a mid-ocean ridge here and plates that move off to the left and the right, which are just modeled as wedges of rigid material. And this the fluid mantle beneath is going to respond in some way to the divergence of these plates. And the solution which you get for an isoviscous mantle is this so-called corner flow solution. The mantle is upwelling and then turning a corner and moving off to the sides with the plate, producing this negative singularity in the pressure for an isoviscous case. And Dan and Mark showed a long time ago that if the parameters are in the right regime, that negative singularity can cause the magma to be focused toward the ridge axis. And so these are streamlines of the magma with the solid in the background. And within some region, which is understood from the calculations, those streamlines are bent towards the ridge axis, and that magma is presumably then erupted, as a mid-ocean ridge lava rather than just freezing back into the mantle. So, again, this is a classical result, and ideas have evolved a lot, but it still illustrates a very fundamental part of the problem, which is that the solid flow can set up pressure gradients which the liquid responds to over potentially large length scales. And then it's just a matter of adding in the numerics, and you can really solve more complicated problems involving melting and more complicated non-isoviscous mantle rheologies and so forth, and produce these kinds of solutions.
Rich, the colors there are the melt porosity?
That's right. This is, sorry, this is the volume fraction of melt going on a logarithmic scale. So here it's 0, but we plot that as less than 0.1%, up to white, which is greater than 10%, but you don't really have any of that. So, you know, really these are of the order of 0 to 3%. Well, there's interesting features of these models, but I don't. Maybe if you want to talk about this, we come back to it at the end. The last thing that I was going to mention is reactive flow. I think this is the last kind of fundamental behavior of the equations, which it's worth keeping in mind as we go through the week. You start with a porous medium, and of course the melting and the mass transfer between phases that takes place is not like the melting of an ice cube, which is made of pure water, right? But it's the melting of a multi-component solid, and the solubility of the different components of the solid is a function of pressure and temperature. And one of the key dependencies is the solubility on the basis of pressure. And so this was an experiment, a mathematical experiment, where they just said, well, let's have a solubility in the liquid of some soluble component which is going to increase as you go up in height. So some depth in the mantle, say 60 kilometers, and as you move towards the surface, the solubility of some component increases, and therefore melt that percolates reacts with the solid, removes that component from the solid, increases the mass of the melt relative to the solid, and this is called reactive melting. And as with the case of these shear instabilities, this process is unstable, and so where you start at the bottom of the domain with here's porosity, with a uniform porosity, you can spontaneously produce localizations where melt will preferentially flow through and react in these channels where you have more melting, lower pressures, and convergence of melt streamlines. And diverge away from these regions that are more compacted in between. You can see that divergence of the solid phase where there's already more melt. Is there a sign? There may be a sign shift in there. Oh, sorry. Let's not dwell on this. But in any case, there's this channel instability. This was early work on this. There's been a lot more since. Here is a dispersion relationship. So we see that unlike for the shear band case, there's a maximum, and so we expect these channels to emerge on something that's a little bit smaller than the compaction length, which is right. There's the wavelength equal to the compaction length. And again, to keep you awake, here's a numerical simulation where we're looking at the porosity, and you can see these channels coming and going with time, and porosities of between 0 and 10%. And here's the residuum. So this is the concentration of the soluble phase, and it's initially roughly uniform, but as the magma percolates through and reacts, the soluble phase gets stripped away, leaving some places where you have no soluble phase, and other places where the residuum hasn't seen that much melt transport, and you have solid phase. And this is on length scales which are smaller than the compaction length, and potentially related to patterns that we see in outcrops of mantle, which are thought to be places where there was melt transport, where you have regions of pure olivine called dunites, which are like these blue patches, and regions in between where you still have pyroxenes that haven't been dissolved away, these yellow patches. So I'm going to skip over this last part and come to the key challenges. What I've shown you has been known for decades, and as people come to the field, I think it's really crucial that they understand that the equations have certain characteristic behaviors, which, as you add complexity to the models, will be modified but won't go away and can therefore become tools of interpretation. But the models that I've showed you were all very simple. They threw away vast amounts of important physics, and they aren't going to be able to really reproduce the observations. And so we're left with a lot of key challenges, which I think is what motivates this program and what brings us together for this workshop. And so here are just some key challenges, and I don't claim that this is an exhaustive list, but some of the things that I think we should all try to keep in mind as part of the big picture of what this field is struggling with. So validation of theory against the laboratory experiments. These laboratory experiments are really well constrained. They're really well observed, and they provide us some robust constraints. And comparison against the laboratory experiments is a great opportunity to gain some insight into how the material that we're interested in works. We ought to be looking for the capacity to make testable predictions of strong proxies. It's not enough to just solve the fluid mechanics, because we won't be able to have observations of the velocities and directions of melt flow in the mantle. The mantle is just too inaccessible. And so we need to be able to convert those solutions into predictions of proxies like geochemistry, of erupted basalts, like seismic or magnetotelluric measurements that will be coming out and improving in quality over the coming years, such that we can check whether the models that we're producing are actually consistent with the natural systems. So by making these predictions of strong proxies, and by strong I mean things that can actually help you distinguish between different hypotheses, then we can validate theory against natural observation. One of the basic observations tells us that there's a very rapid timescale of melt transport. Mantle convection is slow. Mid-ocean ridges move slowly, but melt seems to move very fast, and we see that from a variety of different measurements, which I don't want to go into, but it's not fully understood why that is the case, how these porous flow solutions can give these really rapid timescales. And so, that needs to be, I think, a theme of research in the future. The grain scale is much more complicated. It looks like anisotropy may be important. We don't understand how localization can take place in the mantle, and yet we see very strong evidence of localization. And so something's going on at the grain scale that we probably don't fully understand, including the evolution of grain size itself. So that's an important part of the problem. And then, of course, the chemical and petrological complexity. The mantle is more chemically complicated than most models so far have handled, and also is more rheologically complicated. And in particular, when you get down to lower temperatures and you start to have interaction between the magma and the lithosphere. And to accomplish all of this, we need solutions, and we need to get them in a sort of time period in which sensitivity studies and analysis of the results can be done. And therefore, we need to accelerate the numerical models to enable long-time evolution of large domains and resolving these fine features. And while we can hope that with computational power and improving algorithms we can do this, I think it's probably also worthwhile keeping an eye on developing new strategies to handle these multi-scale challenges. Maybe we won't resolve all of the length scales of interest and all of the time scales of interest, and we need to somehow parameterize or model those in different ways. Mantle heterogeneity is this sort of maybe the elephant in the room. I mean, the chemical variations in the mantle may be very large and significant to the dynamics. And then, of course, applying this where we actually have observations in subduction zones above mantle plumes, in the deep mantle, less observations, but nonetheless, and in the context in which the hypotheses can be tested. So I think that's a long enough set to keep everyone here busy for quite a long time, and I'm sure I've left out a lot of important problems, which I'd love to hear any response to this, what's done or not done among this list. But that's what I hope we'll be talking about this week. So sorry for the massive review for certain of you, but I hope this was helpful in getting us off to a start on a sort of level ground. That's it. Thanks.
Any quick questions for Rich before we go to coffee?
Yeah.
Sure.
Could you show the last slide?
Oh, sorry, I took that down already.
You listed lots of challenges. The first one, I think you wrote a sentence from the point of view of a theorist.
Yeah, definitely.
Yeah,
I didn't want to.
Experimentalist, and what I like theorists to do is to validate experiments in terms of the applications, because when we do experiments, particularly deformation experiments, to produce like shear bands, and all the experiments we can do are human timescale.
Yeah.
Scaling is a serious issue.
Yeah.
We can find beautiful microstructures, but I'm not sure how we can extrapolate this. And then, to do that, we need a theoretical diagram. So I think, it looks like validation of theory against laboratory experiments. It looks like laboratory experiments are truth, and then theory. No, we do something within our limitations. But going from laboratory to us is a big step. So that's really needs theory.
Yeah. Actually, I think that we'll address that directly this week in a couple of talks. So thanks for raising that.
But maybe a comment on that. The problem is that, from what I understand, that they cannot even model the experiments as they are. So using something that does not work at the experimental scale to extrapolate to the Earth is a problem.
I think that's maybe excessively pessimistic. We can all go home. Let's just forget it. I think that's excessively. We do get certain parts of the experiments right. I mean, and I think that the models are also evolving to handle some of the challenges that are the inconsistencies. So I think we can say something, but maybe I'm biased. It's a reasonable point.
Any other thoughts? Doug?
Yeah, several of you have been here since February, so I was curious if you have like sort of a greatest hits or like greatest surprises or greatest breakthroughs that you've made so far.
Thanks for saying that. I guess I would have really liked to have been able to do that. That was kind of what I had hoped, but life intervened. I was at the workshops, but I haven't spent as much time here as I would have liked. I hope that at the end of this week we're going to have a wrap up, and we'll try to pick up some of those questions. And I mean, I know that this is not a very reasonable thing to say, but a lot of the lectures are online, and so if things come up and we're referring back to previous lectures, you can go take a quick look and skim through and find the parts that are of interest. I think it wouldn't be a good use of time for me right now to try to recap what's been a varied and interesting program. I think really gaining momentum in the last month as well. So. Okay.
Okay, should we go to coffee? We come back at 11:30.
Thanks.